Today, lesson 23B, exponents, putting it all together, and that's exactly what we're doing. We're putting together all of the rules and all of the simplifying and performing operations with exponents. We're going to add a fourth exponent rule towards the end of the lesson today. So let's go ahead and get started. I would like everybody to go ahead and do 1 through 4 on your own, and then we'll have you shoulder partner those, and then I will talk about all 4 of them. Go ahead and do all of 1 through 4. So for number 1, I know that most of you know that this is 1 over x to the 5th, y to the 7th. The reason why is because this means this by the rule of negative exponents. That's supposed to be a positive. And then this right here is 1 over y to the positive 7. And if you multiply those two things together, we get 1 over x to the 5th, y to the 7th. I do realize most of you just jump straight to that, and that's fine. Number 2, a very similar idea. The long way of getting there is that this means 1 over c to the 3rd power by the rule of negative exponents. We are multiplying that by d to the 4th. If you want to think of that as d to the 4th over 1, that's fine. But that's how we get d to the 4th over c to the 3rd. And once again, I realize many of you jump straight from the problem to that, and I'm okay with that. Number 3, once again, similar idea. This is 7a to the 7th times 1 over b, because b to the negative 1 is 1 over b. If you want to think of that as over 1, that's fine. And like the previous problems, many of you just jump straight to that, and I am okay with that. And then number 4, another similar idea. This means 1 over 3 to the 3rd. This means xy squared. This means 1 over z cubed. If you want to think of this as over 1, you can. And then multiply straight across. You get xy squared over, and remember I mentioned this yesterday, we're no longer leaving a base that is a number to an exponent like that. We need to figure out what it is. That's 27. So xy squared over 27 z to the 3rd. Any questions about 1 through 4? Yes?
So the only time you can leave it with the exponents on is if it's a letter instead of a number?
Yeah, or unless the instructions tell you that it's okay to do that. Yeah, we're going to end up with one. I think it's number 6. I think is number 6 the one with a bunch of 4s in it?
Yes.
I'll let you leave that one because you end up with a fairly large exponent. Okay. Number 5. I want to talk very quickly about what you should be thinking in your mind about number 5, and then I'll have you do 5, 6, 7, and 8. What you should be thinking about in your mind is grouping your x's together using the commutative and the associative property, and grouping the y's together and then dealing with it that way. That's what you should be thinking about in your head before you jump straight to the answer. All right, go ahead and do 5, 6, 7, and 8. I already talked about the fact that you should be thinking about grouping like things together, and I had written down x to the 5th times x to the negative 6. That's x to the negative 1, and then y to the 2nd times y is y to the 3rd. And then from there, we have x to the negative 1 times y to the 3rd. That becomes a problem like in 1 through 4. So that would leave us with y to the 3rd over x for number 5. Number 6, this one is in here for a reason, and the reason is very simple. Some of you seem to think that this simplifies to 64 to some power. And my question to you is, where did you get 64? I don't see any 64s up there. If I think about this the long way, this is 4 times 4 times 4 times 4 times 4 times 4. 6 of them. I am multiplying that by 1 over 4 times 4. And this is 5 4s that we are multiplying together. This is, once again, from the other day, extended products. And so and then once again, this is the long way of getting there. But what I have is I have 11 4's on top and 2 on the bottom. So that means both of these on the bottom will cancel out with 2 of those on the top. Or you could have gotten there by using the property of multiplication, where you are supposed to add exponents when all the bases are the same and it is a multiplication problem. That, of course, is the fastest way to get to 4 to the 9th power. Yes?
Some people got 64, I think, because they multiplied all.
No, I know how they got it. I know how they got it. But the point here is that there aren't any 64s up there, and it's almost thinking of it like this. You know, if you had x to the 5th times x to the 7th times x to the 3rd, the answer to this is x to some power, right? The x doesn't change. The base here doesn't change, so why would it have changed in this problem? But that's a common mistake when the base is a number, to want to multiply all of those bases together. But that's not what really is happening there. And I understand why people jump to that conclusion. And they do that because of what they're doing in number 7. Because they see that, well, look, in this problem, I have to multiply the 4 and the 5 together. That's true. But the 4 and the 5 are not bases. They are coefficients. So we don't multiply bases together. We multiply coefficients together. And then we have an a to the 2nd times a to the 3rd. That's a, because if we thought about that, we add exponents when we have the same base and we're multiplying. And then b to the 3rd times b is b to the 4th. So number 7 should be 20a b to the 4th. And then number 8, we can sort of deal with this one the same way we dealt with number 7. 4 times 3 times negative 2, those are coefficients. And then x times x cubed is x to the negative 2 times x squared, that's x to the 0, which is just 1. So we don't have any x's in our answer. We have y squared times y squared, that's y to the 4th. I'm multiplying that by y to the negative 4. That's y to the 0 power, which is 1. So we just end up with negative 24 for that one. Any questions on these 4 problems? All right, let's continue on here. I will do number 9 for you, and then I'm going to have you try the next 3. There are lots of ways of dealing with number 9. You could think of it this way, using the law of negative exponents. This first part could mean that, and this could mean this. And then we could get to the answer from there. But we could also use the rule of a power to a power. What do we do with exponents when we have a power to a power? Same thing here. Now we have a situation where we have a multiplication problem. What do we do with the exponents when we have a multiplication problem? Can I leave my answer like that? Yes or no? No. We typically in math don't leave things with negative exponents. So 1 over t to the 14th. All right, I would like you to now do 10, 11, and 12, and then we will compare those with our shoulder partner. All right, so we've already dealt with number 9. Let's take a look at number 10. I'm going to do this one several different ways. Let me start. I'll come up here. One way is thinking about the rule of negative exponents. That turns into that. And then from there, you could think about the denominator like this. And why am I going back to extended products? Well, it's very simple. I saw some of you who forgot to deal with that 2 as the coefficient in what is now the denominator. So you should be able to see at this point that it's going to be 1 over, we've got 2 times 2 times 2 is 8, and y to the 4th times y to the 4th times y to the 4th is y to the 12th power. Okay? That's one way of looking at it. Another way, and Lucas asked me about this, he asked me if this negative 3 goes with the coefficient as well. And it does. And that leads us to our fourth exponent rule that's on the back side. You could kind of think of this in terms of the distributive property, but the exponent goes with each part. So if I split up 2y to the fourth as 2 times y to the fourth, the negative 3 as an exponent goes to both parts. Well, 2 to the negative 3 is 1 over 8. And y to the fourth to the negative 3 is y to the negative 12, but y to the negative 12 is this. And you can see I still get to where I need to be, which is 1 over 8y to the 12th. Any questions about number 10? All right. Number 11 is just an extension, really, on number 10. So this, I could think of it as 3w to the negative 5 times 3w to the negative 5 times 3w to the negative 5 using expanded product, and then times 4w to the second times 4w to the second. And now I can multiply all of my coefficients together. Could somebody do that, please? 4, is it 432?
Yeah.
Okay. And then now I've got all these w's, and I'm supposed to add exponents when I'm multiplying. So I've got negative 15 there. Negative 15 plus 4 is negative 11, but I can't leave the expression like that. It should be 432 over w to the 11th. Now notice that sometimes I'm using the rules and sometimes I'm going back to expanded products, and it's based on what I saw when I was walking around the room. All right, and then number 12, more of the same thing. I'll use the power to a power rule right there. That gives me a to the 9th. In this one, I'll think about it in terms of an extended product. So I've got 5a to the negative 5, x to the second. I'll move the other one out here. And so I've got 25 by multiplying the coefficients together. Right here I've got a to the negative 10. And here I've got x to the fourth. And so I've got 25 x to the fourth, and then my a to the negative 10, a to the 9th, that's a to the negative 1, so that's going to put an a down here in the denominator. So 25 x to the fourth over a. Any questions with number 12? Yes?
Question about number 10.
Make sure you go all the way through number 18. Number 14, we can think about this a number of different ways, but one way would think of it as two problems in one. C to the second over C to the third times D to the negative 3 over D to the negative 1. And I know many of you don't have to think about it that way, but that's really what's happening. And this part right here is 1 over C, and this part right here, remember we subtract exponents when we are dividing. Negative 3 minus negative 1 is negative 2. So we have times d to the negative 2, but remember, d to the negative 2 is 1 over d squared, so we basically have 1 over c times 1 over d to the second, and that would give us 1 over c d squared. Number 5, there seemed to be a little bit of discussion about this one. It's obvious what's happening with the 8 over 2, but this can be thought of as 8 over 2 times 1 over c to the negative 3. 8 over 2 is obviously 4, but the discussion was what in the world's going on here? Well, this could be thought of as 1 over c cubed. And what happens in a situation where you have 1 divided by 1 over c cubed is that part just ends up being c cubed. So we have this is equivalent to that, so we have 4 times c cubed or 4c cubed for number 15. Number 16, I'm not going to do it step by step here, but this is 1/2. This, if you subtract the exponents, you get d squared. Now, here's another issue for some people. They get d squared, they see how that's d squared, because this becomes d squared. But the question for them sometimes is, I don't know whether that goes on top or on bottom. Here's how you can tell. Do you have more d's on top or on bottom? What? Top? How do you know? I don't think I've still heard what I want to hear.
Is it bottom because
No, it's top.
Oh, okay.
The reason is because negative 9 is bigger than negative 11, right? I know that's hard to see when both numbers are negative, and I think that's what Peter was trying to say there. But if you have more on top, that's one little trick of recognizing that the d squared has to go on top. So it should be d squared over 2. And number 17, thinking about it exactly like the previous problem, we end up with 2 over 5b squared. Any questions with that one? I didn't work it out because it's really a combination of 15 and 16. And then number 18, once again, a combination of previous problems should be 3d to the 5th over 4c to the 2nd. All right, any questions about that group of problems? Cambry?
Can you follow step by step number 18?
So if I do this part right here, that's a fraction that reduces to 3/4, right? This part right here. If you subtract exponents, you end up with c to the negative 2. Or you could do that little trick that I just said. Do you have more c's on top or on bottom? You have more on the bottom, so they have to be on the bottom. But you'll see how that works out. And then here, d to the second over d to the negative 3, that's d to the positive 5. And so this turns into 1 over c squared. So here's what we end up with. You kind of see that now?
Yeah. For some reason, when I simplified 48 over 64, I got 716.
Ah, okay. All right. Any other questions? All right. So let's go to that fourth exponent rule, and that's the power of a quotient property. And to me, this is more like a common sense property, and it also banks off what Lucas was asking about earlier. If we think of extending that exponent to every part on the inside of the parentheses, we get x to the a over y to the a, just sort of pulling that exponent into every part. So let me go through 19 and 20 really quickly, and then I'll have you try 21 and 22, and then we're finished. So if I split up 3x over 5, all of that squared to this, from there it's just simplifying the way that we already know how. 3x times 3x on top is 9x squared, and then on the bottom, 5 times 5 is 25. So that simplifies to 9x squared over 25. Let me now do number 20 for you. I like following the order of operations. And the order of operations tell us to simplify inside of parentheses before we deal with exponents. So based on what I just said, the only real thing that I can simplify is that part right there. Because a to the negative 2 is 1 over a squared. So that technically, as we just talked about a few minutes ago, would move that a squared down to the bottom. And if you multiplied it all out, that's what you would see. And then from there, we just use this power of a quotient property and write it out like this and simplify the numerator and simplify the denominator. All right, so let's end today with you doing both. Number 21 and 22. I guess what I should make sure of is this. Do all of you know what to do with a big fraction like that with a negative 2 on the outside? Yeah, it has to do with what we talked about yesterday, right? It's the reciprocal. So if you do the reciprocal of what you have on the inside of that parentheses, that negative 2 becomes a positive 2. So it turns into something like this. All right, I'll let you take it from there and then do number 22. First of all, nobody asked about, I went ahead and did the first 2 steps, but nobody asked about where that went. Well, just like the previous problem, that's 1 over b cubed. And when you think about that, that's the reason why it suddenly appears on top now. And it's 2ab cubed over 3. Now, remember, negative exponents represent division, or sometimes we can think of that in terms of reciprocals. That's why I took this and flipped it over, and then the outside exponent became a positive now. And I wanted to do that because now that makes it easier to use the power of a quotient rule. Pull that exponent in and make sure we do it to everything. And so that should be 9 over 4a squared b to the 6th. Now that leads me now to number 22, because this is where I saw some issues. I saw some of you flipping that upside down, or doing the reciprocal to the positive 2 power, and then using the power of a quotient property. If you did that, you totally missed the first thing that I said when we started problems a few problems ago. Anybody know what I'm talking about?
First?
No.
Simplifying inside of parentheses?
Yeah, if you don't do that, if you don't take that strategy, you're going to end up doing way more work than you need to. That's just following the order of operations. Can't you do some simplifying inside of here? Yes or no?
Yes.
Yeah, and some of you did not see that because I saw this huge number in the numerator and a huge number in the denominator, and then you were trying your best to try and reduce that thing. That's a mess. Simplify within the parentheses first, because now look what happens. This is much, much easier to deal with just by simplifying within the parentheses first. Now you can do the reciprocal. Now use the power property for quotients, and then simplify. So that's what we should end up with. All right, any questions? Yes?
Will the